Now we're going to solve systems of linear equations by using the elimination method. So here we have two linear equations. And when we use the elimination method, we pick one of the variables that we want to eliminate so that we may solve for the other variable. In this example, I'm going to pick the x's. Now, how we eliminate these two x's is we want to make sure that we have exact opposites. We want the coefficients to be exact opposites. So, it'd be pretty easy to change this top equation to a negative 1x. And I'm going to do that by multiplying the entire equation by negative 1. So we're going to distribute this negative 1 and then rewrite the equation to the right. So that gives us negative x plus 2y equals positive 4. Notice how all the signs changed. And then I'm going to rewrite my second equation just the way it is, but right under the first one so that I can add. Now notice, here's what I wanted to do. I wanted to get these two x's to be exact opposites of each other, which they are, so they will cancel when I add these two equations. I get 5y for the two y's and equals 5. And now dividing both sides by 5, I get that y equals 1. So now I have my y-coordinate of my solution. So we're going to pick one of the two equations and substitute that y-coordinate in for y and then solve for x, which is what I did with the second equation here. And you notice that I get x equals negative 2. And so these two equations, which are lines, they're linear equations, so their graphs are lines, we're finding where the two lines cross, where they intersect, and it's at a point negative 2, 1. And let's check our solution. And we're going to check it in the other equation, the one we did not use to solve for x. I'm going to substitute in my negative 2 for x and my 1 for y into the equation and see if I get a true statement. Notice how I get minus 2, which is negative 4. Okay, let's try this again. Here's my next set of linear equations, our next set of lines. We want to find where they intersect. This time, rather than getting rid of the x values, I'm going to get rid of the y values. So looking at that 3 and that negative 2, if I could change those to 6, then I would have my opposites. So I'm going to multiply the top equation by 2, and I get 2x plus 6y equals 2. Then I'm going to multiply my bottom equation by 3, and I get 3x minus 6y equals 18. Notice that my y's are exact opposites, so I can add these two equations. And I get 5x equals 20. And dividing by 5, I get x equals 4. Now, how I decided on that 6 was that I looked at the 3 and the negative 2, and it's almost like finding a least common denominator with fractions. It was easy to change 3 and 2 to 6, so that's why I chose those. Okay, now I'm going to go ahead and solve for y by substituting my x equals 4 into my top equation. And then that gives me that y is negative 1. So these two lines cross at the point 4, negative 1. And let's check that by using our second equation and substituting our solution. 4 for x and negative 1 for y. And let's see if we get a true statement. And it looks like we do. 4 plus 2 does equal 6, so that checks. All right, in this exercise, we want to determine whether the system of equations has no solutions, one solution, or infinitely many solutions. And the previous equations we used, we found systems with one solution. Now let's see what happens here. We are going to get that, let's eliminate the y's. So we need that top line to have a negative 6y, so that when I rewrite the bottom line under it, my y's cancel. And so I multiply the top equation by 2. And now I'm rewriting my bottom equation. And now look what happens here. The x's and the y's both reduce. They cancel to 0. And I get 0 equals 0, which is a true statement. So this tells me that my system has infinite number of solutions, because what I have here are two lines that are really basically the same line. So all of the ordered pairs on the lines satisfy both equations. So we have infinite number of solutions. This equation, again, we're going to eliminate x this time, and I need a positive 3 to match my negative 3 below, so I multiply the top equation by 3, and I get 3x minus 6y equals 9. Then I rewrite my bottom equation, get negative 3x plus 6y equals 9. Again, I notice that both my x and my y's are canceling, but on the right-hand side I get this time an 18. So 0 does not equal 18. This is a false statement. So this system of equation has no solutions. And if you were to graph those two lines, they would be parallel lines that never meet. And that's the case where the system has no solutions.